Hello and welcome to today's video. In this video we're going to talk about the sector area of a planar curve. Now you will recall that we've talked about that topic before in connection to polar curves, and we will now generalize this result to general curves in the plane. So this is called sector area of planar curves. Let's first recall what we know already. Now, given a setup like this, we have a curve given in polar coordinates. So that might look something like this. We have two angles, starting angle phi 1 and end angle phi 2. We want to calculate this area here. That's the area that we need to talk about. Then this area is given by a formula we have devised in one of the previous videos. So for a polar curve, the sector area between angles phi 1 and phi 2 is given by the integral from phi 1 to phi 2 over 1/2 times the radius as a function of the angle phi. That's what defines the polar curve, squared d phi. Now the question is, what about other planar curves? Planar curves given in Cartesian coordinates and or in different parametrizations. Now we make this a two-step process. Let's talk about the parametrization first. Now, what about if we don't have phi as a parametrization, but something else? Then, if that is the case, let's say we have a curve, gamma, some parameter interval I, and that curve maps to R2. And let's say we can still use polar coordinates to represent that curve in a way, but the angle is not directly the parameter. So it's still a polar curve, but the angle might not be the parameter directly. So let's say the curve is given as gamma of t. T is our parameter now. Equals t. And again, t is a transformation from polar to Cartesian coordinates. We have some radius that depends on phi. And now the difference is phi also depends on that parameter t. So t parameterizes phi and phi parameterizes r, right? And we have phi of t here as well. And again, remember that t here, t of our phi, that was our transformation given as radius times cosine phi and radius times sine phi from polar coordinates r phi to Cartesian coordinates. Now if we have something like this, what we can do is we can use the rule of substitution to compute that integral here. Remember, general form of the rule of substitution here. So we have an integral to compute over an expression looks like this. A function f at g of t. So we have the outer function f, the inner function g. And if we integrate that times g prime of t, dd, then that's the same thing as integrating f of x dx. Usually the rule of substitution is stated the other way around, so you start with this here, and you start with this here, you come up with the inner function, you find that there indeed is this t prime here, more or less directly, and you end up with an integral that looks like this here. And of course you also have to adapt the boundaries of the integration, so if you integrate from t1 to t2 here, then here you would have to integrate from g of t1 to g of t2. So it would be the corresponding x values here. Now, how can we apply that in our situation? Well, basically, what we have is this here. And what we want is this setup here. So we want to go from this side to this side in that case. So that's a little unusual, but if we just apply that formula more or less directly, we would say the f here, this here corresponds to r of phi, right? So our f corresponds to r of phi squared over 2 to be precise. That's our function f. I know that is f, and phi in turn is a function of t. Then what does that mean for the left-hand side here of our equation? Well, it means is we have f of g of t, right? So basically g corresponds to phi of t. So what we get here is our r of phi of t squared over 2. And now we have to multiply by g prime to make this correct. So what is g? Well, g is phi of t. So we need to multiply by phi prime of t. So that's the left-hand side of our expression. And that means the area that we want can be computed as the integral from t1 to t2 over 1/2 r of phi of t squared times phi prime of t dt. That's the first step of the process. Now you'll agree that a curve is seldom given in that way. So if you have a polar curve, then usually, of course, the angle is the parameter and not something else. If something else is the parameter, then usually the curve is not given in polar form. So you don't have a function as the radius as a function of the angle. So of course we need to take this one step further. And now that's step 2. Let's say the curve is given in Cartesian form, Cartesian coordinates. All right, so we have a curve, gamma, parameterized by some I in an interval, some t in an interval I. It maps to r squared, so again, a planar curve. And that's given in Cartesian coordinates. So our gamma looks like this. We have gamma of t equals some function x1 of t and some function x2 of t. And we don't have an outright interpretation as phi and radius phi. Now, what can we do? Well, we can, of course, try to transform that back into the polar form to be able to apply this formula here. So what we need to do is we need to find a polar form of this gamma here. And that means basically we need to reverse the transformation. So remember that transformation that was t of r and phi is r cosine phi, r sine phi. So these here are the two Cartesian coordinates. that correspond to r and phi. And now, well, if we want to reverse that, well, these here are the Cartesian coordinates. Let's see if we can compute r and phi from those. So we need to compute r and phi from x1 of t and x2 of t. And of course, r and phi will then be functions of t. Now, how are we going to do that? Well, x1 of t is equal to r cosine phi. x2 of t needs to be equal to r sine phi for the r and phi that we want to determine. And that means, first thing, that means r squared is going to be equal to r squared times cosine squared phi plus sine squared phi, because that here is equal to 1. And now that's the same thing as adding the square of this side and the square of this side. So that's the same thing as x1 of t squared plus x2 of t squared. Right? So the radius can easily be computed. Now what about the angle? That's a little more complicated. For the angle, turns out that it might be a good idea to look at the ratio of x2 and x1. And of course, that also means we have to exclude cases where x1 equals 0. So we're not talking about those right now. But one can easily deal with those cases if the need arises. So looking at this transformation here, x2 over x1 is equal to r sine phi over r cosine phi. And that's the same thing as sine phi over cosine phi, or the tangent of phi. That, on the other hand, means that under certain circumstances, suitable restrictions on the values that are possible, the angle phi, or one possible angle phi, can be computed as the arctangent of x2 over x1. Yeah, and as I said, that works for suitably constrained values of x1, x2, and of course it's only one possible angle that we get this way. There will be others that would do the same job. Okay, so that way we get r squared and we get phi from x1 and x2. And now let's try to use that. So what we want to do is we want to use that for the sector area that gamma covers between two parameter values, gamma 1 and gamma 2. So we have a situation that looks like this here. We have our curve gamma. We don't know the polar representation of that curve, but we know there's a point on that curve here and here. That point is gamma of t1. That here is gamma of t2. Now what we want is the area covered between those two points here, the sector area covered between those 2 points here. And we already know a formula that depends on t, on r, and on phi, so we just have to use that. So that green area that can now be computed as the integral from t1 to t2, 1 over 2, r of phi of t squared times phi prime of t dt. Now basically phi is this arctangent, so what we have to do is we have to compute the derivative of that function here, arctangent x2 over x1. So let's do that first. As an information that We have not yet talked about in detail I'm just giving you the derivative of the arctangent. One can come up with that formula by using the derivative formulas for the sine and the cosine, and then getting that of the tangent, and then using the formula for the derivative of the inverse function to get the derivative of the arctangent. But that's not going to be the main focus of this video, so we're just going to skip over that. And I'm just going to tell you the derivative of the arctangent function of, let's say, y is given as 1 over 1 plus y squared. So if you want to determine the derivative with respect to t of the arctangent of x2 of t over x1 of t, then that's going to be, well, that's a chain rule, obviously, so we have to differentiate the outer function first, the arctangent. So that's going to be 1 over 1 plus x2 of t over x1 of t squared times, and now we differentiate the inner function, which is x2 of t over x1 of t. So we need to use quotient rule for that. So we start with the derivative of x2 prime t times x1 minus x2 of t times x1 prime of t divided by x1 of t squared. And now if we simplify that just a little, so that numerator here can't be simplified a lot, so we are still stuck with x2 prime t x1 of t minus x2 of t x1 prime of t, but the denominator can be simplified a little. So if you look at that here we have x1 of t squared, and here we have x1 of t squared, so that cancels out. We get x1 of t squared plus x2 of t squared. And now let's look at our integral again. This formula here, we do now know phi prime, so we are now ready to substitute our findings into that formula to get a final result here. So our integral from t1 to t2, 1 over 2 r of phi of t squared times phi prime of t dt is now the following. So let's see, we keep that 1 over 2. R squared of phi, we've talked about that already. R squared is equal to, here we have it, R squared is equal to x1 squared plus x2 squared. So we can just use that. And remember that is r squared, so no need to square it again. And we multiply that by phi prime, and we've just computed phi prime as being this expression here. So let's just copy that. And then we need to integrate this dt. And you can hopefully immediately see there's one simplification that we can make. This expression here is the very same as this expression, so that cancels out. And we are left with the integral from t1 to t2, 1 over 2, x2 prime times x1 minus x2 times x1 prime. dt. And that here is the final formula for the sector area of a planar curve between parameter values t1 and t2. So that's for the sector area of the planar curve gamma equals x1 of t, x2 of t between t1 and t2. And this completes this video about the sector area of a planar curve. In the upcoming videos, we'll use our knowledge on curves, planar curves and other curves to integrate along these little creatures. So we'll have some fun with integration along curves. And as usual, I hope I'll see you then.